Well, hello there. So let's talk about functions and structures. This is primarily aimed at writing functions in C and C++ for the Arduino systems. Okay, so hopefully you have seen functions before in a programming language like MATLAB. And so this is a concept that we're just looking at how to do in C++ or C. It's really something used as a programming style. You don't have to have functions for every bit of code, but it makes your code modular. You have little modules that you can reuse. So for reusable code, for easy to maintain code, using lots of functions is generally recommended. The advantage of using a function you can think of like a black box. So something like the sine function, which you use all the time as an engineer, we don't know what code is in there. Somebody wrote how to do the sine function in the language you're using, but we know we give it x, it gives us sine x, and that's all we need to know. So it hides how the code works, makes it so the person can just get the functionality without having to dig into the software itself. So if we think of the function as a black box, it has inputs and outputs. So we can see here the inputs and the outputs of the function. So we don't have to have inputs and outputs in an Arduino function. You can leave these blank. Sometimes on an Arduino, the inputs, rather than being sent through the top of the file, they come from something like an analog to digital input, and sometimes the outputs are running hardware on the chip, so we don't have to pass variables back as output, but the general function does have them. So this line here is what's called the function call. It's how we would use a function in a programming language. So y equals sine x. X is the input to the function sine, and we're calling the function, the sine function, and the output of that function is copied into the variable y. So again, we have the input x, the function name that we're calling, and the output gets copied into this variable. Starting at the top here, with a function in Arduino, you can put them all into the same file. That's the most common thing. You have your Eno file and put all of your functions into that file. In something like MATLAB, it's traditional to have a separate file for each function, and you can do that in the Arduino too if you'd rather. It makes them more modular. In general C, it's the usual thing is to have the function definition before it's called. There are workarounds for this, but Arduino, because it has a wrapper around the program before it goes into the C compiler, you don't have to do this, but you'll see in a lot of cases the functions are at the top, the sub-functions, and then the main function is actually at the bottom of the file. So this is the anatomy of a C function. We have the function name. You have to give it a name here. My multiply function is this one. If you have inputs, you have to give them names that you're going to use in the function. So here we have inputs x and y, and we use them down here in the function. And you have to say what kind of variable. So the variable type. These are both integers, int, variable types, whole numbers. That's how we define the inputs. For the output of the function, you get one output in a C function, and you tell what type of output, what variable type you're going to use here. So this is going to return an integer. You use the return statement and return any integer here, and that's what gets copied out. So in programs like MATLAB, you would give it a name, and that name gets returned, but here we say we're going to return an integer, and down here we say return this integer. You can actually have multiple return statements if you have complicated branching in your function, so this is a little more flexible. This result is a local variable declared inside the function. It's only used here, and then this gets copied into whatever calls the function. A couple of other examples here. Of course, we have the setup and loop functions that are part of the standard Arduino program. They're both void functions, which means they don't have an output. So if we don't want to have it return something, because the loop function, for example, never exits, and the setup function doesn't get called by anything in our program that we can see, so returning something wouldn't be very useful there. They're both void instead of this kind of return function, and they both have empty parentheses here, so they have no inputs defined either. Sometimes you'll see void in the parentheses to confirm that there's nothing, but empty parentheses are fine. Then they have curly brackets for the beginning and end of the function. And then here's a third function in this program called calcdist. It returns a floating point and has no inputs, so void. And it gets data from the analog to digital converter on the Arduino and does some math on it and then returns its calculation. So sometimes, especially in the homework for this class, I'll say write a function. That means something like this. A C function. It has a name, it has a type, it has inputs and outputs. Doesn't mean functionality, doesn't mean write a program that has the functionality. So if I say write a function that reads to analog inputs, you have to have a function outside of loop and setup that reads an analog to digital input or whatever it says to do. So sometimes students think function just means what it does, but a function here is a particular kind of program fragment. So here we're going to go into some examples of taking a program without functions, or with just the basic setup and loop functions, and making them a little bit better programming style by moving the various things into functions that we could reuse or easily change or swap out. So if you don't have any functions, sometimes people call that spaghetti code. It's not a nice thing to have your code called spaghetti code. So people, any kind of hard to read code often gets called spaghetti code. There's a quote, I got this, I should cite it from Wikipedia, but it was cited from somewhere else. Programs that have the same clean logical structure as a plate of spaghetti. So if it's all convoluted, it's spaghetti code. So this is an example program that reads two analog to digital pins. So here int sensor value comes from A0, sensor 2 comes from pin A1. It uses those analog to digital readings and calculates the voltage at each pin. You can see the analog read serial example where this comes from, and then it simply prints out the voltage with some space in between. So on one line you get the voltage and the space and then the second voltage. So very simple program. So what we want to do is make that into modular code so that we can reuse parts and follow along a little bit easier. So this is the first way to make this code modular. So what we have is functions to do all of the work and using global variables to control all the data. So this code is divided into functions and all the variables are global variables. That means they're declared outside of the functions, normally at the top. We have all of our global declarations. So we don't have any inputs or outputs. All of the functions are void and empty parentheses because we're sending everything around with global variables. So global variables are really frowned upon in terms of programming style. It makes the code less modular because you have to use that exact name or else you can't reuse this function. And if somebody's using that name already, you have to go and search and replace and things like that. So global variables are a bad programming style because it really hinders the modularity and the reusable nature of the code, and you have to look up at the top all the time to see what variables are declared, and did I capitalize the V and all of that. But it's actually fairly common with things like Arduinos because Arduinos don't have that much memory, and if you have local variables, as we'll see in a second, things have to get copied and passed around between the functions. So this is the one exception where maybe global variables are not terrible, but do expect some grumbling from the code gurus. So if we look into how this works, again, we're starting down here at loop. This is the main program, the top of our code after setup. Setup runs first, and all it does is set up the serial port, but then it comes down. And so this is the advantage using functions. We can just see exactly what's going to go on. We're going to read the sensors with a function called read sensors, and we're going to do the output with a function called do output. It's going to print out the values. We've got comments and function calls. So this is very readable, and you can see what's going on right away. And then as we want the more details, we can look at the read sensor function, which is defined up here. And we can see what it does. It's basically copying and pasting of the original code and putting everything into the global variables that we define up here. So we read the 2 analog pins, we convert it to voltages, and they just hang out in global memory. Then when this function is done, it jumps into this function, which is the do output function, and it's printing these global variables, so it has access to them. So this is not a bad way to go. It's an easy thing. You could just copy and paste things around. So definitely, if you're new to functions, it's a good starting point. This second example here is using a little bit better style. We have functions that return outputs and receive inputs, which means they're self-contained. All of the variables are local variables, so we don't have any global variables here. So we've divided the old program, the spaghetti code, into functions again, and this is just a slightly different style. So down here in the loop function, we have 2 local variables, v1 and v2, and we call a function called read sensors, and we store v1 and voltage from pin A0 and v2 from pin A1. So we're calling a function twice here. And the reason we have to do that, what we wanted to do was read the 2 pins and output the 2 voltages, but in C you can only return a single variable. So that's the change here. So to accommodate that style, we had to write a function. This read sensors takes a single pin and it returns a floating point. It has local variables where the pin gets saved into this local variable called sensor value. It gets converted into volts in a local variable called volt, and that's what gets returned. So this local variable volt gets copied into V1 when we pass it in A0. So A0 would be pin. We read pin, calculate volt, and then copy volt into V1. And we send A1 in as pin. We read A1, calculate volt, and then volt gets copied to V2. So it's a little different style, and this was just because we had to work around the fact that C can only return a single thing, one variable. The do output function looks very similar, but now we're just passing it, V1 and V2, as inputs to the function. There are no outputs from this function because it's just printing to the serial port. So it does do something, but it doesn't return anything back to the loop. So if we look at the two codes with functions, they're both very readable. We can see that we're getting these variables from the read sensors function, and then we're doing something with them in the output. And this doesn't have any global variables. So for example, this function read sensors, anytime you want to read a sensor and get it in volts and you can't remember, is it a 10-bit or do I divide by 1023 or what, you can reuse this function, put that in all of your code, and then you have it handy to reuse. In a lot of programs like MATLAB functions, you can return more than one thing. So then we could have had a read sensors where we passed it A0 and A1 and it returned V1 and V2. We can do that in programs like MATLAB. If we want to do that in C, the standard workaround is to use something like a data structure, which can hold more than one variable in one thing, and we pass the data structure back. But really in Arduinos, it's much more likely that you'll use a C++ concept of a class or object that is similar to a structure in the way it stores data, but can do more than that too. So let's look at structures, just as sort of an introduction to this concept of objects. This is the C data structure that we're talking about here. This program doesn't have any functions beyond setup and loop. We're just looking at how to use this data structure. So in C, you use the word struct, and then you give it a name, and this defines a new variable type. So often underscore T, just so that it's clear it's a type and not an actual variable, but you can give it any name that you want that follows the C naming rules. And then it has curly brackets, and then inside here we give it the variables that it holds. So it has sensor value, that's an int, and voltage, that's a float, and pin, that's a pin, that's a char. And those are all stored inside this single structure. So one thing holds 3 variables, and they're all different types. So it's like a little database or something. So then here, when we want to use that, we use this now as the variable declaration. So instead of float or int, it's this new structure type, and then we give the actual implementation of it a name. So my ADC is the name of a variable that is this data structure type. And then to use the individual parts of the data structure, you use a dot. So my ADC dot APIN is A0. You've probably seen this kind of dot thing. It comes up a lot in C++ as well. So my ADC dot sensor value, we have something called sensor value, and we want to access it to read it or write it. We can just use the name of the structure and the name of the part of the structure. So data structures are a way to work around the passing a single thing limitation. There's an example on our class webpage of doing that, but it gets a little more complicated. And if you really want to use this programming style where you don't have global variables, I do recommend probably going to a C++ class, which extends this beyond storing data. You can also have things like functions and initialization all bundled together into a C++ class. And we'll look at that in the next lecture on libraries. So just a little bit about programming style. There are different ways to design software, and if you're working in a team, then your manager's going to have ideas, and these are just a couple of general ideas. Top-down programming style means that you start with the main functionality, the main things that your code has to do, and you write that. So if you look at our loop functions in the other examples, they're calling these functions that read sensors and do output, things like that. So we think about the big things that have to get done and put in placeholder functions, right? Short functions that just say, I got to the sensor part, and then we can look at how the main function works, the main code going, and test our skeleton code, and with really placeholder functions that just say I got here or do something very simple. Then once that's working, you go back for each placeholder function and integrate it. So you do all of the sub-functions second. Another way to design software is the bottom-up approach. And here you would write the functions first. So you'd say, well, I need a function that reads all the sensors. I need to drive some motors. I need to do all these things. So you would write those, or you could hire them out. If you're working on a team, you could divide the work, and then each function gets tested. And then once they're all working, you can integrate them into the main program. You can do both. You can start with the main code and some functions. If you're working on a team, people can be working on different parts of this. Both of these, the big advantage is that you're testing incrementally. You're not writing the whole program. You're writing simple things that you can test. If there's a bug, you know it's in this little part that you're testing. So in the top-down, your main code working with very simple placeholder functions. So if there's a bug, you know it's in the logic of the main code. In the bottom up, you're testing each function on its own with some sort of test main program that's calling it. So both of these are testing incrementally, and that's really the big thing that you definitely always want to do. The naming of top-down and bottom-up in C and C++, the functions often are at the top, the sub-functions at the top of the file, and the main skeleton code at the bottom. So top-down means you're actually writing the bottom code first, and bottom-up means you're writing the sub-functions, which are at the top of the file first. Nothing I can do about that. It's just the way things work. So you don't have to organize your C file that way, but but often you'll see that. So top means top level functionality. Bottom up means sub functions, the low level things first. So just to show you, here is one of the examples that we looked at with the global variables. If we were going to do a top-down approach, we would write this main skeleton first. We would put names for all of our functions, and then in order to compile it, we actually have to write these functions, but we'd write some placeholders that just say, I'm in the read sensors function, print them out to the screen. If we were going to do the bottom up, we would think about all the things our program has to do, and we'd write these functions, the read sensors and the do output, and test them individually in their own little separate test programs. And then once they're done, we can put them into our main program, and the whole thing should more or less work. Or if there's a bug, we know it's not in this thing that we tested, it's in the new program that we've written. So both approaches let you test incrementally. All right, so that's it for programming style. I hope that was useful. And the next lecture, we're going to look at Arduino libraries, which brings us into C++ classes and some object-oriented programming ideas that go along with Arduino. See you in the next video.